Hello everyone, welcome back to the another lecture. So this is a part 2 of our hysteresis control. So in the last lecture what we have seen the hysteresis current control. What is the working principle of hysteresis current control that we have learned. Then we have seen that it's a variable frequency type of the control and its frequency, switching frequency is depend upon certain parameters, right? Then we have implemented the same control in MATLAB and we have simulated the things for the buck converter, and we have seen that we get the better response as well. So this is how and what is the control logic and all that we have learned. Now to make it more advanced, we can make it a two loop control. Like first loop is our voltage loop and then we can use the current loop, and for current we can make the hysteresis band, right? So this is how you can see here control block diagram. So hysteresis loop is for current now, and my there is another outer loop which is that is the error of the reference voltage minus actual voltage, which is passes through an PI controller, and that will generate some my current reference. Okay, so I will tell you this logic and all once we go in detail of this video. So today we will see the hysteresis current control of the buck converter. When this particular control is very important, when we have the tight regulation on the current. Okay, that time if let us say my load current I want the 5 ampere as a fix, that time I can go for hysteresis current control, so that I can make my current within some particular hysteresis band, and that current is locked in that particular hysteresis band and it will operate in basically that band only. So that time we mostly prefer the hysteresis current control. Okay, and it is more accurate and more basically advanced than the hysteresis voltage control. Okay, so now let's get started with this video. So hysteresis current control. So again, the hysteresis current control is a type of a non-linear control technique that our inductor current is regulated within the predefined hysteresis band. So same kind of waveform. So I will keep my inductor current between IH and IL, and this is a 2 delta, that is the peak to peak ripple in the inductor current. So let us say if my reference is 5 ampere, I want peak to peak ripple as 1 ampere. So I can basically allow it to go for 5.5 to 4.5. So this is how I will manage, adjust my overall control structure. Okay, now again it is very simple, fast responding and commonly used in the power converter for voltage regulation. So these basic things we know. Now we will move forward. So what is the operating principle? We have learned for the voltage hysteresis control. The same kind of operating principle is there for current hysteresis control as well. So when my reference minus delta L, that is a lower band, when my actual inductor current is lesser than this lower band, then that time I will switch on my basically MOSFET or switch. That time inductor current will increase with the slope of M1. So this slope is M1, I guess, and because the inductor current is increasing and inductor current is charged, inductor is charging, that time my output voltage will also going to be increased. So I have basically, by controlling my inductor current, I am making my voltage as well constant within that particular band. So M1 is dIL by dt when it is on time. So we know how to calculate the M1 and M2 for buck converter, boost converter, buck boost converter, right? Second thing, when switch is off, that time when I will make the switch off when my inductor current tries to go above this particular band. Okay, that is IH band. If it tries to go above this particular band, that time I will switch off and my basically inductor will discharge, and that time I discharge, that means my inductor current will decrease and my output there also by decrease. Okay, so this is the overall operating principle of the my voltage current hysteresis control. This thing we have already seen how the control and all. Now again the expression for the switching frequency. So switching frequency expression remains the same. Okay, either you take the IH or VH. Okay, so only difference is basically we need to add one more voltage block, right, and one PI controller. That is the only difference. Apart from this, the switching frequency of this particular IL and IH remains the same. Okay, that is Fs. This expression we have seen. Okay, during the on time, what is my on time? Delta by M1. So delta is my peak to peak ripple and M1 is the slope, rising slope. M2 is my falling slope and delta is my total overall hysteresis band, that is a peak to peak ripple. Okay, in the current I will say is for this particular time. So based on that I can calculate my total switching frequency, and this is actually the switching frequency you will get, okay, when you implement this. Now this expression we have already seen, so you are much more familiar about this expression of the switching frequency. Now we will move forward. Now overall control block diagram I am going to explain to you right now. Okay, and then this control block diagram we will implement in the MATLAB and will run the simulation for the buck converter. So you can see that I have my basically DC to DC converter. So I have some actual voltage, right? So what I will do, I have my some reference voltage, let us say 7 volt, 10 volt. So reference minus actual I will pass, that will generate some error. That error I am basically passing through the one PI controller block. Now how to find out the KP and KI block for this particular case? So we know that for buck converter, boost converter, buck boost converter, we have learned the small signal modeling as well. Those videos are there on my YouTube channel, you can go and watch. So what thing we need when V out reference by V out actual, we have to pass. So that time our PI controller, what is the how to calculate the KP and KI? So we know we need the V naught by IL parter, right? So if I have the expression for V naught by IL parter, then by doing that I can tune my PI controller. Okay, what things we need to make sure that its a KP should be greater than its KP and K. How we calculate? Its a phase margin should be greater than 55 degree and gain crossover frequency should be FSW by nearly 100. Okay, so this is the requirement we have, right? So this thing we have seen, right? What is the requirement and all for basically tuning this particular block, how to calculate the KP and K value. Once that is done, then I am getting here some actual reference inductor current. Then that is I am adding with the delta I. Delta I here in this case is my half of the hysteresis band. So I am adding the delta I here and delta I here. One time I will add, one time I will basically subtract. So I will get two limits. Okay, IH and IL. Then those things I will compare with the comparator and I will compare my IL actual. So IL actual I will give here and I will compare this with my upper hysteresis band and lower hysteresis band. Then based on that we will set and reset our SR flip-flop and basically output Q will be generated. So this is how the overall control block diagram is. So now what we will do, we will go in the MATLAB window and there basically initially we will see the script. And then again I will explain you one time like how we have calculate the this particular thing. Okay, so how we have tuned this particular thing. Okay, that thing I will explain you, and then we will go in our Simulink model and there I will run the simulation. So I will just move to the another window. So here we are in our MATLAB script. Okay, so this is the same script I am using for buck converter. Only thing is that for this particular application we are now doing the current hysteresis control, right? So I have keep my output voltage requirement as 5 ampere as constant. Okay, so there is a some sort of load which need only 5 ampere as a constant. Okay, and I am keeping my output voltage as 7. So actually overall my power will be, so I have calculate what is the value of the R will come and all. Okay, so here R is my V out by V in. Based on that, that load is in such a way that it will only accept the output of 7 volt and output current of 5 ampere. Okay, so this is how I have structured my specification. Okay, based on that I am again for designing of L and C I am using the 200 kilohertz as my switching frequency, but you know that switching frequency is a different thing. Okay, when you use the hysteresis control. How and what factor it depend and all that also we have seen. Now I have calculated the LNC. Now I wanted to design the controller. So you see the block diagram, right? I have discussed with you. So what first thing is there? One PI control is there, right? So what is the actual transfer function we needed for that PI controller? So we need a V out by IL. Okay. So how this particular transfer function? So you can see here, right? So what is coming from here? V out. What output it will give this PI controller? IL reference. Okay. So what transfer function I need? V out by IL. Right. So this transfer function I need. Okay. So I have shown you also in one of the lectures of ours, that is where I have discussed the important transfer function of ideal DC-DC converter, where I have actually discussed with you like how we can do the small signal modeling and all, then how to derive the transfer function. So and we have derived few transfer function. So now these are the important transfer function of buck converter using the small signal modeling. Now what transfer function I want? I want V naught by IL, right? So where is V naught by IL? So directly we don't get V naught by IL. So what we need? We need V naught by initially D. Okay, V naught by D, and again one more whole divided by I will need IL by D. Okay, so d will cancel out and I am getting whatever transfer function I want. Okay, so I am getting the V naught by IL. So I have V naught by D transfer function available here. I have IL by D transfer function available here. So I will write it down both this transfer function first and then I will divide them. Okay, and if I will do that, basically I am getting my overall transfer function. So the same transfer function I have also written down in the script file. You can see that initially I have written down V naught by D. Second transfer function I write IL by D. Okay, so you know how to write it down this transfer function and all in script that I have already discussed with you. So numerator, denominator, so I have one transfer function V naught by D and second transfer function IL by D. Then I have divide both of them to get the V naught by IL. So I have my overall transfer function. Now what we will see after after writing the transfer function, we will see its pole zero plot. Okay, so right now we don't need to see the pole zero plot. What we are more interested in, it's actually phase margin, gain, crossover frequency. This thing we are very much interested. So I will just see the V naught by IL's margin. So I will just run this particular script so you can see the margin, how much margin it takes, how much margin it giving and all. So that thing we will see. Okay, so it is just running, it is calculating the margin. Okay, so it is showing the margin. Now what is the phase margin? It is showing 136. Okay, but we want less than 90 degree or up to 90 degree, that is fine. So what is ultimate target of our is it should be always greater than 55 degree. Okay, but what is its frequency? Okay, what is its gain crossover frequency? You can see I have assumed that my converter operates at 200 kilohertz. So when I tune my outer loop, its bandwidth should be FSW by 100. So I want the bandwidth nearly about the 2 kilohertz, right? So what is the bandwidth as of now? So bandwidth is 24 kilohertz. My converter I am assuming operating at 200 kilohertz and its bandwidth is showing as 25 kilohertz near me. So that thing I don't want because inner loop should be faster as compared to the outer loop. So I want FSW by 100, at least this much of lower bandwidth I need. So it comes near with the 2 kilohertz. So I want my controller bandwidth should be around the 2 kilohertz. So now we have seen the margin. Now what I have done, I have added one controller, that is a KP and KI. You know how to add this value and all. This thing I have fundamentally explained to you in my previous videos, like how we can come with some few iteration, how we can come nearer and nearer to the KP and KI value. Okay, and once I have added the controller, now you can see that, so I have not tuned very that much, so there may be some disturbance you can see in the simulation, but if you can spend more time to do the controller tuning properly, then you will get a very good result. Okay, so I have added one controller. I will just run this particular thing. So after running this, you can see that what is the margin and all I am getting right now. So it is just running, just wait a bit. So now you can see that what margin I am getting here. Margin again 95 degrees something, so that is okay for me. Okay, but it is main thing is what is my this particular frequency now, gain crossover frequency. So it should be near less than 2 kilohertz. If I am getting, that is I am accepted. Okay, because this much what I want. Otherwise there is a mismatch between the outer loop and inner loop, right? So you can see that what is I will change the unit to kilohertz. So its bandwidth is curving around 0.2 kilohertz. Okay, that is fine. It is very less bandwidth, but this will work for my case because I'm not tuning that properly, but I have told you how to tune it more accurately. Okay, and phase margin again you can reduce, make it less than 90 degree by adjusting the parameters again, KP, KI. So you can achieve that particular thing, but I am not doing here. With this value also I am getting satisfactory results. So we have tuned the controller part, KP, KI, everything, right? So what value near about we can take, that I have told you. Now I will go in my basically particular simulation model. So you can see that again my buck converter is there, which takes the PWM as my duty as a input, and it will drive this MOSFET, and then overall working will be happen. Here in this case I am not applying the load transient because my load requirement is fixed. So now what we will see the control block. Okay, so this buck converter model you know already, and what I said that I am not applying the load transient here because my load requirement is fixed. In this particular case I want 7 volt as my constant output and 5 ampere as a constant current. Okay, so that is why I am not changing the load here. So I am keeping the load what is actually calculated. Now control logic again same. I have my reference voltage minus actual voltage. which is I am passing through the one PI controller, and what is the parameter of the KP and KI I have taken, those things we have right now basically tuned. So the same KP and KM I am using here. Okay, now this particular thing, what we will do, it will basically generate the IL reference. Okay, this is what it will generate. It will generate the IL reference. Now this IL reference, what I have done, I have added the lower band and upper band as lower band upper band limits. So I have creating the two references, separate references. That is my lower band reference and higher band reference. This is based on how I am, what particular delta I band I am keeping. So now what delta I band I have keep here, you can see here in the script. Delta I band I am keeping as 0.5, like mean 5 ampere is my actual desired output current. So 5 ampere plus 0.5 and 5 ampere minus 0.5. So it will be, it should vary from 4.5 to 5.5. So this is how it should come. Okay, then I am adding the actual inductor current. So this actual inductor current coming from here, and then again the same hysteresis control logic I am using, and that is I am going to give to my SR flip flop, and based on that I will generate my PWM signals. Okay, now I will run the simulation and show you what exactly the output we are getting. So I am running the output, okay, simulation. So you can see that simulation started, and you within very quick time, no, it is just evaluating the blocks, and after evaluating it will simulate, and how much time it takes to reach to its steady state. You can see that it is started from some 9.8, okay, and it will take some time up to I guess 0.04 seconds to settle at 7 volt. Okay, so this is my desired output. Now I will show you in the scope. So what is, you can see the current as well. So the output current is 5 ampere. Why? Because we have keep the load requirement in such a way that my output current is 5 ampere and output voltage is 7 volt. Okay, so this thing we have seen here using the average block. Now I will open my scope. So you can see here output voltage is again 7 volt, you can see here, and output current is again, you can see that some nearly from 5.5 to 4.5 it is going, and output current again the same band. So this is how actually this particular control works. So if I will zoom here, okay, so you can see there is some disturbance as well here. This is because of the our control. This control will work in such a way. So if you see that you can see, so it is coming nearly from 5.5 to 4.5. So this is how actually this controller work, and output is again nearly 7 volt. Okay, now if you calculate the switching period, so this is your task, how to calculate the time period you in this particular thing you learn. Okay, and you write it down in comment box that for this particular simulation sir, time period was coming near with this. Okay, so just you calculate this time period, how much time period is coming, and how this time period is different from actual. These all things we have seen. Okay, so this is how actually this particular simulation work and this control work. So I hope so you understood. This is again running, so I will just stop the simulation. We don't want it for a longer duration. So this is how this control block diagram in here, and this is how we will use it. So now we will move forward. So thanks for watching this video. I hope so this two video you understand about the hysteresis control, like how the voltage hysteresis control work, how the hysteresis current control will work, and in future if you want to implement these two particular controls, you will easily implement. Okay, so thanks for watching. Stay tuned for the next video.